All right, let's talk about one of the most famous charts in all of science, the periodic table. But first, I want you to forget everything you might have learned about memorizing it. Seriously. Instead, I want you to think of it as a map, a powerful, predictive map of, well, pretty much the entire universe. I mean, really think about that. What if you had a cheat sheet that could tell you, just by looking at it, how different materials would behave, what they'd create, what their personalities were? Well, that's exactly what the periodic table is. So let's start unlocking some of its secrets. So how does it do all this? How can it be so predictive? Well, its incredible power really just boils down to one fundamental rule that governs its whole structure. It's the secret code that makes the whole thing work. And this is it, the periodic law. Now that sounds a little dense, but all it's really saying is that an element's properties repeat in a predictable pattern based on its number of protons. Put it even simpler, where an element lives on this chart tells you how it's going to act. Its position isn't random at all. It's its entire chemical resume, all right there at a glance. Okay, so the first and most obvious division on this map is a super simple one, left versus right. And this one big split reveals the two fundamental types of elements and their, totally opposing personalities.
Over on the left side, we've got the metals. You can think of these guys as generous. They have these outer electrons that they're just not that attached to, so they're pretty happy to give them away. And that freedom, by the way, is exactly why they're so good at conducting electricity. But then you look to the right side, and you've got the nonmetals. And they are the complete opposite. They are stingy. They hold on to their electrons for dear life, and they are always looking to grab more from anyone else.
And this whole tendency to pull on electrons, yeah, it's got a name, electronegativity. It's basically an atom's pulling power in a big chemical tug of war. And honestly, if you can get your head around this one idea, you are well on your way to understanding so much of chemistry. It's that important. And this is where it all comes together in one beautiful master trend. As you move across the table, from the bottom left to the top right, electronegativity gets stronger and stronger. The metals on the left, they have super low pulling power. The nonmetals on the top right, their pulling power is absolutely off the charts. This one trend basically defines the entire chemical landscape. So we've seen the big picture. Now let's zoom in a little. By looking at just a single column, what chemists call a family, we can see this periodic law working in really beautiful, predictable detail. So let's meet the halogens. Elements in the same column are like family because they have really similar electron setups. And for the halogens, that means all of them, every single one, is just one electron short of having a full outer shell. This shared, desperate need for just one more electron makes them act like a super close-knit family with incredibly predictable behaviors. They're all what we call strong oxidizers, which is just a fancy way of saying they are experts at stealing electrons. And as you move down this family, you see this perfect gradual change. At the top, fluorine and chlorine are gases. Go down one step, bromine's a liquid. One more, iodine's a solid. And their oxidizing power, their ability to snatch electrons, it also decreases step by step as you go down. It's just a perfect, elegant demonstration of the periodic law at work. This quote just sums it all up perfectly. Fluorine sits at the very top right of the table, making it the undisputed champ of electronegativity. It is the ultimate electron taker. Nothing, and I mean nothing, can take an electron away from fluorine. It only takes. So the periodic table gives us these amazing, predictable rules. But, chemistry also loves to get weird. And sometimes, to make things work, elements have to get really creative and, well, they have to break the very rules that seem to define them. So yeah, what does happen when an element just doesn't have enough electrons to play by the standard rules of bonding? Does it just give up? Of course not. It gets clever. It invents a whole new kind of bond. So let's meet our little rule breaker, diborane. You've got 2 boron atoms and 6 hydrogen atoms. Now, if you do the math and count up the electrons they have available for bonding, you come up short. There is simply not enough electrons to form the standard bonds we all learned about in high school. It's a total puzzle. So what gives? Well, the solution is one of the strangest and frankly coolest concepts in all of chemistry. Get ready for this, because it's a bit of a mind bender. It's called the 3-center 2-electron bond. Instead of a normal bond where 2 electrons hold 2 atoms together, this bizarre bond uses just 2 electrons to glue 3 atoms together. Wild, right? So here's how it works. Boron is what chemists call electron deficient. It can't form enough of those normal two-way handshakes with its neighbors. So instead, it forms this incredible bridge. A single pair of electrons gets sort of smeared out across three atoms, two borons and a hydrogen in the middle, holding the whole thing together. It's a brilliant, incredibly efficient, and totally bizarre solution. So the periodic table is our cheat sheet. No doubt about it. It gives us the rules, the trends, the power to predict. But then you get cases like boron, and they remind us that the table is also a map to the exceptions, to the mysteries, and to the absolute frontiers of what's possible. And it just makes you wonder, if elements can literally invent new ways to bond with each other, what other incredible chemical secrets are still out there, just waiting to be discovered?